This application was created, using as a base, 4 components of the methodology Lean Automation. 1. The spin component, that generates the default project, with all the reports on the header. 2. The industrial substation, that generated a substation, with 1 line, 1 transformer, and 2 collector circuits. 3. The component wind power, that generated 2 wind farms, each one of them with 3 wind turbines, and 1 anemometer tower. 4. The component of asset availability that, in this case, was used to analyze the asset availability of the substation base. After generating the base application, were created several reports and KPIs, associated with the optimization of production, and operation, of the wind farms, as will be shown next. One click on the object leads us to the screen associated with it. When clicking over the GE wind turbine, we navigate to the detailed screen of this turbine, where are shown its real-time data, like real power and the estimated one, the capability curve and the real power graph, the estimated one and the wind speed. Now, we will navigate to the Suzlon wind turbine, that seems to be stopped because of the red color. The initial screen looks like the previous one, with real-time data and the capability curve of the wind turbine. There is a failure warning, and one click over it. Takes us to a failure diagnosis and corrective actions screen. When navigating to an anemometer tower, we have data of wind speed in 3 levels, with identification of maximum, minimum and average, besides the pressure, temperature, wind direction, solar irradiation and humidity data. The indicated buttons allow to navigate to a screen, with the totals associated with these farms, where the colors red and green indicate if the farm operates with 100% or not of its capacity, respectively. Navigating to the farm total screen, with GE wind turbine, we have a pizza graph, with active power versus the reactive one, a trend graph, with the maximum active power, the current one and the minimum one, as well as the values of the power factor, the active power and the reactive power, respectively. Navigating to the substation screen, we have a line bay, a transformer bay, and 2 collector circuits, each one associated with a farm. To see more details of the substation, see the video of the industrial substation component. The Reports button contains 12 screens with KPIs, reports and dashboards, whose objective is to generate data to optimize the farm production and operation. The first graph shows the magnitudes from the current month, with its real production and the estimated one. The second graph shows the behavior of the anemometer tower for the selected period. The tower and period are selected, and the graphs show the minimum, maximum and average values of the wind speed for the 3 levels on the selected period. On the third screen, besides selecting the anemometer tower and the period, it's possible to choose between 4 graphs. The first, the wind rose, shows the predominant direction for 6 wind classes. The second shows the predominant direction for the average wind speed. The third graph shows a counter of events by wind direction in the period. Finally, the fourth graph shows a counter of events by wind classes. The fourth screen shows, for a chosen month, the average speed of the wind of a given day, and the energy produced on the same day. The fifth screen shows, for the chosen period, the capacity factor for each wind turbine selected. As well as the factor for each one of the two farms. In the sixth screen is made, on the upper part, an analysis considering the estimated and real power of each wind turbine, of each farm, on the entrance of the collector circuits, and on the line bay of the substation. In the end, it shows the total loss, and the system indicates which element has the lowest efficiency. On the bottom part of the graph, select one sector and one period, and a loss analysis is done for this sector for the selected period. On the seventh screen, the power curve analysis is made for each wind turbine, from its characteristic curve. One period and one wind turbine should be chosen. The upper curve, calculated using the IEC 61400 norm, show in blue, the characteristic power curve of the wind turbine, considering the wind speed, and in green, the measurements made. If the measurements are inside the acceptable margin, the power curve is okay. If it is not, the bottom right curve does the power analysis versus the rotor rotation curve. If this curve is not adequate, we can say that the problem is in the gearbox or the generator. If it is okay, the bottom left graphics does the pitch angle versus the wind speed analysis. The comparison of this curve allows us to identify a possible problem in the pitch motors or in the control system. The eighth screen shows, for each wind turbine, for a chosen month, the MTTR and the MTBF. The ninth screen shows, which faults caused the bigger number of stops, and which faults were waiting the most for fixing. The 10th screen does the type of stop analysis, regarding frequency and duration. That is, a stop not necessarily is a failure, it can be a lack of wind, preventive maintenance, etc. Finally, the last two reports are associated with the electrical assets availability analysis. In this example, 4 bays are analyzed, a bay of line, of transformer and of collector circuits. If we make the transformer bay unavailable, we also make the 2 collector circuits unavailable. We do an opening and a closure of the transformer circuit breaker, and in sequence, we show the collector 1 availability. Further details in this report, and in the 3 dashboards shown, can be seen on the video that shows the component asset availability, AMS.